So some people have asked me for a more complex example of where you might use an FPGA. So I have an example here which incorporates an FFT, a Fast Fourier Transform. And the application here is a frequency detection system. Okay, so let's say you have an electromagnetic wave which comprises of multiple frequencies, or perhaps you're doing harmonic analysis on a machine or a structure, and for some reason you wanted to know if there was a particular frequency within that signal. And if you detect that frequency, you wanted to let the user know by perhaps flashing an LED or something like this. Well, we can do this in an FPGA using the FFT mega function. And if you're not sure what an FFT is, I think this is a good way to explain it. Let's say you have something which approximates a square wave like this in red. Now this would be performing a 6-point FFT, and essentially what that means is at each frequency point you would do a correlation of a pure sine wave at that frequency with the signal you're comparing with, in this case the square wave. If there happens to be similarity between those two signals, well, that indicates that there's quite a lot of that frequency component within that signal, and that would appear in the frequency spectrum as a spike, a high value. If there's not so much of that frequency component in the signal, then it would appear as a low number in the frequency spectrum. And essentially an FFT is just a correlation of several frequency points, several pure sine waves at different frequencies with a particular signal. So this is how you would describe it mathematically. Basically, an FFT uses mathematical tricks to try to speed up the process. So whenever you need to do this kind of thing computationally, you would use an FFT. So in this example, we're using an FFT. We'll use a 4096 point FFT. So if we go back to this example, we would have 4096 sine waves at different frequencies, and we would correlate each of those 4096 sine waves with the incoming signal. Of course, it's worth noting here that the signal has to be windowed, so the FFT performs the function on windows of the signal coming in. Okay, so it splits the signal into windows and performs the FFT on each one of those windows. So let's have a look at the system again. So we have a 4096 point FFT. Now if we use a 40.96 megahertz clock, that would give us 10 kilohertz frequency resolution, and that basically means that each one of these sine waves is separated by 10 kilohertz. So if we're looking to detect signals, we can basically detect a signal to within 10 kilohertz, and we'll take a look at that a bit later. So let's have a look at the design. I think the best way to show you this design is with the netlist viewer. So the first thing we have here is the phase locked loop. If you're not sure what a phase locked loop is, it's just a way for you to convert a reference clock signal, in this case 50 megahertz, into a different frequency. So in this case we convert the 50 megahertz clock into a frequency of around 40.96 megahertz. So that clock frequency goes into this FFT wrapper. Now when we use an FFT, the FFT mega function, we have to provide the mega function with interface signals, And I mentioned that the FFT is split up into windows, and basically we have to tell the mega function what our window is. And the way that we do that is with a start of packet and an end of packet pulse. And the window of data basically fits within those two pulses. So within our wrapper, that's one of the main things which is happening. So let's take a closer look. So this is the control module. And as I said before, the main purpose of this module is to produce a start of packet signal which comes out of here, and an end of packet signal which comes out of here. And the way we do that is we have a 12-bit counter, and we say if the counter is equal to 4095, then we'll make the end of packet equal to 1. If the counter goes back to 1, then we make the start of packet go to 1. So that gives us a start of packet and end of packet which is separated by approximately 4096 clock cycles, which is exactly what we want for an FFT of that size. So that's the control module. This is the FFT itself. This is essentially the FFT mega function in Quartus. So we can have a look if we can drag this up. So if I double click here, sometimes this doesn't work. I think there's a bug with Quartus actually, but maybe it's because I've got Signal Tap running. No. Okay, sometimes it doesn't allow you to get the FFT mega function back up. But essentially we have a 4096 point FFT, and that is taking data from the A to D converter. And I should say at this point that the A to D converter that we're using in this project is with a daughter board which connects to the Cyclone V starter kit, and we're using one of the 65 megasample per second A to D converters on that daughter board. I think the logic for that is up here. So that's the logic which is driving the A to D converter. Now this is a parallel A to D converter with 14 bits, and we're driving it at the same frequency as the FFT, which is 40.96 megahertz. So the signal from the A to D converter comes out of that module here, and it comes around, well actually that's the input signal. The output signal is this one, ADC out, and that goes all the way around here, back across here, and then into the control module. And the control module just basically passes that through. And we can see that here, it's just a pass through. Okay, so there's actually no need to pass that signal through the control module, but that's what I've done anyway. Okay, so the output of the FFT is a complex 4096 point sequence. So it comes out of the FFT one sample at a time. And by the way, it goes into the FFT one sample at a time too. But you know, if you have 4096 samples going in, you'll get 4096 samples coming out. And basically those samples are the correlation strength for each of those frequencies. So that's what we have coming out. We also have coming out of the FFT the start of packet from the source. So this tells you exactly when the first sample from the FFT comes out. And of course the first sample of an FFT is actually DC. But we can use that actually as a reference because later on we'll want to know exactly what the correlation strength is at each frequency. So what we'll do is use the start of packet coming out of the FFT as a reference point, and that will go into this counter, and basically when the start of packet comes in as a 1, so it's a 1-bit pulse, that will reset the counter to 0, and the output of that counter is basically a count from 0 up to 4096, and we can use that actually to work out exactly what values correspond to what frequencies. Okay, so as I said, the first one that comes out will be the DC. The second one that comes out will be the 10 kilohertz, because we have a 10 kilohertz resolution. The third one that comes out will be 20 kilohertz, then 30, then 40, then 50, all the way up to 4096 times 10 kilohertz. So we can use that actually in this parallel to series module. And what this is doing is, if we zoom in here, this is just looking at the value of the counter, and it's saying, it's actually using if statements, and it's saying, okay, if counter is equal to 6, we know that's harmonic number 6, we know that corresponds to, say, 70 kilohertz, and what we can do is use that to populate another variable which is associated with that harmonic. So those values, I think I've got it here for about 15 frequencies, and those values, those harmonic values, go to a threshold module. So all these modules are exactly the same, and inside these modules we have basically an if statement, which is comparing the value of those harmonic signals with a reference value. And the theory is, if the incoming signal is greater than the reference value, then we'll basically make the LED light up, and that will signify that we have a significant amount of energy at that particular frequency. So we've got the same thing going on for around 15 different frequencies. Okay, so let's zoom out again and see if I missed anything. So let's close this. But you can see here how useful the RTL viewer is for actually making sense of the design that you've made. Now there's one other thing. The signals come out of the FFT as complex values. We're not really interested in the complex value. What we're interested in is the magnitude of each frequency. Okay, so the complex value might also give you the phase, but we're interested only in the magnitude of the signals coming out. Okay, so if you recall, if we have a complex number, that means we have the real and imaginary values. So if one of our signals coming out was that means we would have a real value of this and an imaginary value of this. All we want is the magnitude of that frequency. And of course, the way that we can get that is just by basically using Pythagoras' theorem and squaring and adding those two complex components together. Now, if you were doing this properly, you would also have to square root that value. But in this case, there's no need to do the square root, because we can just change the threshold value accordingly. Okay, so we've explained the design from a high level. Let's have a look at the code as it appears in Quartus. So this is the phase-locked loop. So we have an input clock of 50 megahertz. We have an output of 40.96 megahertz. The code which is driving the A to D converter is in this block. The FFT wrapper is within this block. We can take a quick look at this one. So this is the instantiation of the FFT. This is the control module, which we discussed before. So that produces the output of the FFT. Then we have two multipliers and an adder. So that converts the complex FFT output into a magnitude. That goes into this parallel to series block, which is converting the sequence of inputs. So they come in sequentially, so harmonic 1, harmonic 2, harmonic 3. So that picks off those harmonics one by one, and depending on where they fall in this count, which is synchronized to the start of packet from the FFT, we can determine exactly which outputs from the FFT correspond to what frequency. So once we get those values, we can use the threshold block here to check if they're above a particular threshold. So let's have a look inside. So all we have here is an if statement, which is looking to see if the signal coming in is greater than a threshold value. If it is, we'll make the LED go to 1. If it isn't, we'll make the LED go to 0. And that's basically it. That's the system. So I have these output pins connected to the LEDs on the Cyclone V board, but that's basically the system. So we can program the board, hook it up to a signal generator and see if it works. Okay, so here we are at the bench. So this is the Cyclone V starter kit. Hasn't been programmed yet. So that's connected to this daughter board. So this is quite a nice daughter board. It has two 125 megasample per second DACs, which I'm not using in this project, and it also has two 65 megasample per second A to D converters, and I'm actually using one of these now. So this is connected up to channel A, and that's being connected up into the FPGA through the high-speed mezzanine card here. And this is connected up to my signal generator. And if you recall from earlier in the video, we know that we have a 10 kilohertz resolution. So we know that 130 kilohertz will be basically harmonic number 12. And the way I've done it is I've wired up the first LED on the right here, which is LED 9. That one is connected up to harmonic number 5, I think, or 6, I can't remember exactly now. And it goes up from there. So it's harmonic 6, which is 60, 70, 80, 90, 100, 110, 120, 130, and so on. I think one of the LEDs isn't working for some reason, so it might skip one of them when we do the demonstration. Anyway, let's go ahead and program the board. So I'm in the programmer here. So we should see the board program. We're currently set to 130 kilohertz, and we can see one of the LEDs is on. Okay, good. So let's now go to 120 kilohertz, and then 110 kilohertz. I think that's the one that's not working. 100 kilohertz, 90 kilohertz, 80 kilohertz, 70 kilohertz, Okay, I'm just going to scroll through them now because I think one or two of these LEDs are not working. But I'm just scrolling up and down. And I think one of the things I'll do here is have a frequency sweep. So I'll sweep, oh, I can't do it from channel 2. Okay, we won't do a sweep. What I will do is, because I've got both channels of the signal generator on at the moment, I'll connect two separate frequency sources, and we'll see if both of those frequencies are detected at the same time. So I'll just connect second channel. So channel 1 is on 80 kilohertz, and channel 2 is on 120 kilohertz. And we can see it's detected both frequencies. So that one would be 80, and then we've got 90, 100, 110, or 120 kilohertz. So it looks like this is working quite nicely. Now, one of the other things I wanted to do here was have a look at what happened in between those pure frequencies. So if one of the frequencies of the FFT is at 120 kilohertz, that's all well and good. It's going to detect that frequency very well. But what happens if we have 125 kilohertz? So what I'm going to do is just slowly increase. Well, I'm going to go to the 80 kilohertz channel, and I'm going to go to 81, 82, 83, 84, and you can see it starting to go off. That's 85. Okay, and if I carry on going up, 86, 87, 88, 89, 90, and then the next one comes on. So this seems to pick up the frequencies plus or minus 3 kilohertz. And that's kind of what you expect with an FFT, because if your sine wave is not right in the middle of one of the bins, it will spill over into the two adjacent bins, and that's something to watch out for with an FFT. But this seems to be working very well. What I'll do is go to channel 1, and I'll do the frequency sweep. So if I start the frequency sweep at 50, stop it at 200, and we have a 1 second time, you can see that it's sweeping through the frequencies. I can make that go a bit faster. 2 seconds, 3 seconds. No, sorry, that's a bit slower, isn't it? So that's taking 3 seconds to sweep through. I can make it go faster. And what's happening inside the FPGA now is it's performing basically a real-time FFT. So for 4,096 points, it's doing that within a fraction of a second. So this is working very, very quickly. So it's not missing anything that's coming in, even if the frequencies are changing very quickly. Okay, so I think that is a success. I'll make these design files available for you. So I'll put the archived project on Learning Central for you to look at. I hope you enjoyed that video. So this was just a look at something a bit more complex. This would have real applications, whether it was for sort of analyzing the harmonic response of a machine or a structure, or looking at the frequency content of a radio wave. But this is what FPGAs are capable of. So thank you. So yeah, good.